In this work, we find the direct map that determines the modular space integrands for one-loop superstring amplitudes in terms of the field-theory loop integrands. And we can represent the coefficients in the integral for superstring amplitudes in terms of the one-loop BCJ numerators in the integrand of super Yang-Mills and supergravity amplitudes. The integral for one-loop superstring amplitudes on genus 1 Riemann sphere or on torus can be represented in such chiral splitting formalism, where we leave this loop momentum unintegrated. The advantage of such formalism is that the integrand gets factorized into a holomorphic part and an anti-holomorphic part. And this integrand's I will be the main object to be studied. The basis of these I functions is composed of the G functions generated from the Kronecker Eisenstein series. So these G functions has a single pole when Z equals to 0. Therefore, when we integrate these G functions over these punctures, we can get the Mendelssohn variables, the channels that we want. So you can imagine this adds the torus generalization of the 1 over Z on a sphere. We should also require the monodromy invariance of the integrand, saying that the integrand has to be unchanged when we take the ith particle going around the torus. Therefore, the combination of G's that appear in the integrand has to be monodromy invariant. Now let's consider the field theory limit. In the limit alpha prime to 0, the integral is dominated by the region tau to I infinity. So here the torus becomes generated to a nodal sphere, where there's an extra pinch on the torus. And this pinch is equivalent to adding 2 extra vertices on the sphere. So it's called the nodal sphere. And in such degeneration limit, the G functions above get reduced to this cross ratio formula. On the other hand, this ansatz mapped to a nodal sphere has to be expanded into this Park-Taylor formula. And the integral on this Park-Taylor formula over these punctures will produce a basis of one loop scalar integrand. Therefore, these coefficients of the expansion has to be the BCJ numerators in the loop integrand of super Yang-Mills or supergravity amplitudes. So here we then set up a map between the torus integrand and these BCJ numerators. So let's see how this algorithm works in practice. At 5 point, the integrand I can be expanded into such formula with undetermined coefficient C. And we find that through the algorithm described above, these C coefficients can be uniquely fixed by the BCJ numerators. However, starting from 6 point, we also need to consider the monodromy invariance, which will fix the coefficients of terms of some higher G functions. So in general, we have these two inputs, the field theory limits and the constraints from monodromy invariance on torus. They altogether fix all the coefficients